Welcome back to the Deep Dive. This is the show where we take that stack of sources you've sent our way and, well, we synthesize it all into the most potent knowledge you can get in one sitting.
And today we are really getting into the weeds on truly scalable AI customization. Because look, large language models are incredibly powerful, but making them work for a specific use case,
Right.
like creating a model that's amazing at drafting specialized legal documents or something, that used to be reserved for, well, organizations with basically infinite money.
Exactly. And that's our mission today for you. We want to give you the shortcut to mastering efficient LLM customization. Because the classic approach, the brute force fine-tuning method, it's just computationally and financially impossible for almost everyone.
It's a crisis of scale, really, and the solutions are just brilliant.
Okay, so let's unpack this. We're going to hit 4 key areas today. First, you have to really understand the colossal problem, the storage and operational nightmare of trying to customize these huge models.
I'll get into the solutions.
Yes, the genius, low-cost solutions, especially LORA and its whole family of variants that basically fix the problem.
After that, we shift gears a bit, from the how to the what.
Exactly. How do we use these methods for specific goals like, instruction following or even advanced reasoning? And finally, we'll talk about the infrastructure that has to hold all of this advanced training together.
Let's start with that colossal problem, though, because you really have to appreciate the scale of failure of the traditional way of doing things. I mean, back in the pre-LLM era, fine-tuning a model like Bert was pretty straightforward.
Right. You just take the pre-trained model, feed it your new data, and tweak all of its weights.
You'd adjust all of them, yes,
Yeah.
to fit the new data.
It's like repainting an entire house just to change the color of one wall. It works, but only if the house isn't a skyscraper.
That's a perfect analogy. Now, compare something like BERT Large to GPT-3. We're talking 175 billion parameters. To store those model weights alone, even with efficient float 16 precision, you need 350 gigabytes of memory.
That is just immense. To give you some perspective on that, 350 gigs is like, downloading maybe 50 full-length, high-def Blu-ray movies just to store one model.
And if you're a provider, say you're offering a fine-tuning service, that storage problem just explodes. Let's say 10,000 users fine-tune GPT-3 the old way.
Oh, wow.
You're now looking at 3.5 million gigabytes of storage. And if 100,000 users want their own custom versions, which is a pretty conservative number.
You're at 35 million gigabytes. It's completely unmanageable.
And that's just storage. Think about the operational headache. A user might only use their custom 350 gigabyte model once in a while.
But you, the provider, have to be ready to spin it up at any moment, which means loading these massive files into and out of GPU memory constantly. And loading a model that big is a heavy lift on its own.
So yeah, traditional fine-tuning is just not feasible. It's a brute force approach that modern LLMs made obsolete almost overnight.
So we need a smarter way. We need optimization. And this is where parameter-efficient fine-tuning, or PEFT, comes in. And the core breakthrough here, the idea that really asks the right question, is LORA, low-rank adaptation.
The question LORA asks is, do we really need to update all 175 billion parameters to get the model to do a new thing? Or can we get the same result with just a tiny fraction of that?
And the genius move is realizing that most of those original weights, they don't really need to move much, if at all. So LORA says, let's just freeze the colossal pre-trained weight matrix, let's call it dollars, and that it stays fixed.
Right. So instead of changing dollars, we only train these tiny little custom adapters that capture the update you want, the delta dollar.
But you don't store that update directly because that would still be huge, right?
Exactly. That's where the clever engineering comes in. The update is captured by the product of two smaller, what we call low-rank matrices, N and dollars.
So think of it like this. The massive frozen matrix dollars is this perfectly running complex engine. And E-dollars are just two tiny little keys. You can turn them easily, and they just slightly shift the engine's output without you ever having to open the hood.
And the really neat part is how they handle the dimensions. They get the exact same output size as the original update, but with dramatically fewer parameters. And that's because other dollars are configured with this tiny internal dimension, $3, which is called the rank. And that rank dollars is often tiny, like 4 or 8.
And that's the key to the whole efficiency win. You fine-tune these massive models, but you're not duplicating 350 gigabytes every time. You're just storing and updating these tiny little dollar matrices. We're talking megabytes, not gigabytes.
And there's a crucial initialization detail, too. Matrix dollars is usually initialized as a zero matrix.
So at the very beginning, it has no effect. The model starts fine-tuning from exactly where it was.
Precisely. And once that core LoRa idea was out there, the research community just ran with it. It led to this huge family of variants all trying to solve one of two things: either reduce the memory needed during training or just make the whole thing converge faster.
Okay, so let's look at memory first. We've got something called LoRa FA. The FA is for frozen A. What's the benefit there?
Well, even though LoRa makes the number of trainable parameters tiny, you still need a lot of activation memory during the training process itself. So by freezing matrix A and only training matrix B, LoRa FA cuts down on that activation memory, which makes training cheaper and faster.
Then you have things like VRA, which seems like it's for an ultra-low resource situation. They freeze and share a little $1 across all layers.
It's an extreme efficiency play. With VRA, you're only training these tiny, layer-specific scaling vectors. It's incredibly lightweight, but still manages to capture the fine-tuning details for each layer.
Okay, now let's talk about speed and the overall weight problem. Killer I, quantized LoRa, that seems essential here because it attacks the size of that huge frozen dollar matrix itself.
Caloro gives you this massive memory win by using quantization, which basically means representing the numbers in that 350 gigabyte matrix with lower bit numbers. Think 4-bit or 8-bit instead of the usual 32-bit.
And that just crushes the memory footprint. I mean, going from 32-bit to 8-bit is something like a 75% memory reduction. But wait, if you're using less precise numbers, isn't there a big trade-off in accuracy? How reliable is that?
That's the critical question, and yes, quantization does mean a slight loss of precision. But Calora uses some very clever normalization techniques to minimize that loss. And the consensus is that for most tasks, the huge memory savings are absolutely worth the tiny, often negligible drop in performance.
So it's a reliable trade-off. And we also see things that are pure speed optimizations, like LoRa plus K.
Right. LoRa Plus is all about convergence speed. Researchers just noticed that you get to the optimal result faster if you use a higher learning rate for matrix B than for matrix A. It's a simple tweak, but it's a huge efficiency booster.
And finally, LoRa drop. Sounds like some kind of intelligent pruning.
It is. It's based on the idea that not all layers actually benefit from LoRa. So it starts by putting LoRa matrices everywhere, trains for a little bit, and then checks the activation strength in each layer.
And if a layer's activations are basically zero,
it just removes LoRa from that layer. If it's not being used, drop it. It speeds up fine-tuning by getting rid of the parameters that just don't matter for your specific task.
Okay, so that really covers how we fine-tune efficiently. We've solved the storage and memory crisis with PAFT. But that's just the tool, right? Now that we can do it, the question changes from how big is my hard drive to what am I actually teaching this thing?
Exactly. You have to turn an LLM from what is basically a perpetual book writer into a useful assistant that actually follows instructions.
Because a pre-trained LLM, it just defaults to continuing text, right? You ask it, what do llamas eat?
Yeah.
And it doesn't give you an answer.
Not a concise one, no. It might just launch into, what do llamas smell like? Are llamas good pets? It just continues the document it thinks it's writing. It never answers you directly.
So instruction fine-tuning, or IFT, is the process of teaching it that Q&A format. And that's the foundation for what we call supervised fine-tuning, or SFT.
And to do this at scale, you can't have humans labeling data all day. It's too slow. So developers rely on generating synthetic data. Frameworks like Distillable are built for this, and they often use multiple LLMs in a kind of feedback loop.
Walk us through that. You start with an instruction, and then what? You have two LLMs compete?
Exactly. LLM1 and LLM2 generate different answers. Then, instead of a human, a third judge, LLM rates both responses based on, relevance, clarity, safety. The best response gets paired with the original instruction, and that becomes your high-quality training sample.
That generated data is perfect for SFT. But SFT isn't the only objective. We really need to compare supervised fine-tuning against reinforcement fine-tuning, RFT, because they teach the model in fundamentally different ways.
They really do. SFT is what we call an offline process. You have a static, labeled dataset of prompt and answer pairs, and you're just adjusting the weights to match those answers.
And when you say offline, does that mean the model is basically learning from a fixed textbook? It can't adapt to new information?
In essence, yeah. It relies on a fixed set of answers. It's great for getting the model to repeat known patterns, but it can also just lead to memorization, which hurts its ability to handle new problems.
Whereas RFT is an online process. It's not about static labels. It's about getting instant rewards during training.
The model generates an output, a reward function immediately scores how good it was, and the model learns over time by exploring strategies that lead to higher scores. It's less about memorizing the right answer and more about learning a good strategy.
So if you're a developer starting a project, how do you choose? It seems like it all boils down to your data and your task.
It's a pretty clear decision flowchart. If you have a ton of high-quality labeled data, we're talking about 100,000 examples or more, just use SFT. It's the most direct path.
But if you have no labeled data, the next question is the task verifiable? Can a script or a function automatically check if the answer is correct?
If the task is not verifiable, if it's subjective, like which of these poems is better, then you have to use reinforcement learning from human feedback, or RLHF. But if the task is verifiable, like a math problem that's either right or wrong, RFT is perfect. You can automate the reward.
And for those verifiable tasks, that leads us straight to Group Relative Policy Optimization, or GRPO, which is designed specifically for things like math and logic, these reasoning-heavy tasks.
GRPO is a super effective RFT method, and because it uses those deterministic reward functions, it completely eliminates the need for expensive human labeling. It's basically a four-phase loop that turns a text predictor into a rigorous problem solver.
Okay, let's walk through that transformation. Phase 1 is data processing.
You start with a raw data set, maybe a bunch of math problems. The key thing here is you enforce a structured system prompt. You tell the model, think step by step before you answer. This forces it to show its work, to externalize its logic.
Then phase 2, generation. The LLM creates multiple possible answers for each problem, maybe 4 different attempts to encourage it to explore different ways of solving it.
Phase 3 is reward calculation. A reward server takes those 4 answers and automatically scores them using very specific deterministic functions. It might check things like,
Did it match the format perfectly?
exactly, was the final number correct? Were all the numbers in the middle correct? Things a computer can check instantly.
And these checks replace the human entirely and give that immediate objective feedback.
Right. And finally, phase 4 is loss calculation. A GRPO loss function looks at the scores, calculates gradients based on the difference between the good and bad answers, and backpropagation updates the model. Over time, it learns to prefer the steps that lead to the highest reward.
The impact is huge. A base model asked for a square root might give you some random nonsense, but a GRPO-tuned model gives you a perfect answer with clear, structured reasoning, often inside special tags. It learns a reliable process.
And this is where RFT really shines. It's teaching the model how to solve a problem, not just what the answer is. But this power leads us to the final critical topic, the infrastructure bottleneck.
Right, because even the best RFT agent in the world needs a stable, standardized environment to work in.
Oh, we've all been there. You spend weeks getting an RL environment set up, and then the next research paper uses a totally custom API, or your environment breaks when you move it to a different machine. The lack of standardization in the environment itself is a huge problem.
So that fragmentation creates all this engineering overhead. You end up spending more time on infrastructure maintenance than on the actual algorithms.
And that's what needs fixing. This is where a framework like PyTorch's OpenM comes in. It provides a common service-based interface for these RL environments, kind of inspired by older frameworks like Gymnasium.
And the technical solution is pretty clever. It runs each environment in an isolated Docker container, and they all communicate over HTTP. That guarantees it'll work the same way everywhere.
And crucially, this means every single environment has to expose 3 core standard API endpoints. No exceptions.
1 is reset, to start a new task. 2 is step action, to send an action and get feedback. And 3 is state, to just check on the current state of the world.
And that stable, uniform interface just gets rid of the custom API headache. Your agent interacts with a simple game or a complex proprietary world in the exact same way every single time. It just makes everything more efficient.
This whole deep dive has been a journey in efficiency, really. We started with this massive computational crisis and then solved it with the elegance of LORA variants, those adjustable keys, instead of the whole engine swap.
Then we learned how to direct that power using smart data strategies like IFT and advanced learning objectives like GRPO for these really specialized, verifiable tasks.
And finally, we saw how to stabilize it all with standardized infrastructure like OpenEd, making sure our agents can actually run reliably. I think the central takeaway for you, the learner, is pretty clear. Efficient LLM customization isn't about brute force anymore.
No, it's not about who has the biggest GPU cluster. It's about intelligent data modeling and clever parameter optimization. The days of duplicating 350 gigabyte models for every user are they're over.
And that leads to a really interesting thought. If techniques like LORA let us adapt these huge models with just a few megabytes, and GRPO lets us train them with automated, deterministic rewards instead of armies of human labelers.
It raises a pretty important question for the future, doesn't it? If the cost of customizing these models is plummeting, the real value in AI development starts to shift away from just having massive compute resources.
So is the most valuable skill set going forward less about training the next giant foundational model?
And more about designing the perfect synthetic data sets, or crafting those precise, deterministic reward functions that guide the model exactly where you want it to go.
The value is shifting from raw compute to the intelligent design of the learning objective itself. Something for you to chew on.
A perfect place to leave it. Thanks for joining us on this deep dive. We'll see you next time.